Welcome back. Today we're in section 1.6 of our statistics course. We're using statistics by Michael Sullivan, and we're talking today about design of experiments. And in this section we will talk about the characteristics of an experiment, we'll explain the steps in designing an experiment, and we will talk just a little bit about completely randomized design and matched pairs design. Here we go. Okay, first let's get a few definitions and then we'll look at an example or two together. This says an experiment is a controlled study conducted to determine the effect that varying one or more explanatory variables or factors has on a response variable. Any combination of the values of the factors is called a treatment. So we can have more than one explanatory variable, and each explanatory variable is called a factor, and every different combination of the levels of the factors is called a treatment. The experimental unit is a person or an object or some other well-defined item upon which treatment is applied. We call the experimental unit a subject when he or she is a person. It would sound very funny to call people experimental units, wouldn't it? A control group serves as a baseline treatment that can be used to compare to other treatments. So it's very important, and you'll notice when you read medical literature, there's always a control group that didn't receive any treatment or that received a placebo treatment. So a placebo is an innocuous medication such as a sugar tablet that looks and tastes and smells like the experimental medication. Isn't it funny what our brains do to us? Just the idea that you're taking medicine can be enough to make you feel better sometimes. Even if the medicine hasn't done anything, just the fact that you expect to feel better sometimes helps you feel better. So that's why in medical studies there will almost always be a control group that receives a placebo, and that's to offset the effect that taking medicine has on your mind. Now let's talk about blinding. Blinding refers to non-disclosure of the treatment that an experimental unit is receiving. There are two kinds. Single blinding means the subject does not know if he is receiving treatment or not. And double blinding means that neither the subject nor the researcher in contact with the subject knows whether the subject is receiving treatment. So not only can taking medicine make you expect to feel better and therefore you will report that you feel better, but also just the doctor's attitude toward you. If you think the doctor expects you to get better, that can also have an effect. So we often see double-blind studies when they're testing a medication just to eliminate the confounding that occurs because the doctor either projects an attitude that I expect you to get better or I don't expect you to get better. Okay, let's look at an example together. Lipitor is a cholesterol-lowering drug. A study was done to determine the effect of Lipitor on cardiovascular disease in 2,838 subjects, ages 40 to 75, with type 2 diabetes and no prior history of cardiovascular disease. In this placebo-controlled, double-blind experiment, subjects were randomly allocated to either the Lipitor 10 milligrams daily or placebo group and followed for 4 years. The response variable was the occurrence of any major cardiovascular event. Lipitor significantly reduced the rate of major cardiovascular events, 83 versus 127 in the placebo group. There were 61 deaths in the Lipitor group versus 82 in the placebo group. So first question, what does it mean for the experiment to be placebo-controlled? Well, it just means that there was a control group that took a placebo instead of the actual medication. So some subjects received a placebo to eliminate the confounding effects of taking medicine. And what does it mean for the experiment to be double-blind? Well, it means that neither the subject nor the researcher who was in contact with the subject knew whether the subject was receiving actual treatment. Neither the subject nor the researcher who administers the treatment knows who's receiving treatment and who's receiving placebo. Okay, what is the population for which this study applies, and what is the sample? Well, their sample was this group of 2,838 subjects ages 40 to 75 with type 2 diabetes and no prior history of cardiovascular disease. So their population is all people ages 40 to 75 with type 2 diabetes and no prior history of cardiovascular disease. All people 40 to 75 with type 2 diabetes and no history of heart disease. And then the sample would be the 2,838 subjects who came from that population. And what are the treatments? Well, there were only two here. Either they received 10 milligrams of Lipitor or they received a placebo. And in some cases, there will be multiple levels of medication. But in this one, there was just one medication level and the placebo. And what is the response variable? Well, they told us that the response variable was the occurrence of any major cardiovascular event. And is that response variable quantitative or qualitative? Well, the occurrence of an event is either it occurred or it didn't occur, so that's going to be qualitative. So let's go through the steps of conducting an experiment. First, we've got to identify the problem to be solved, and we need to state it explicitly, and it should provide the experimenter some direction to go in. It should identify the response variable and the population to be studied, and it's often referred to as the claim. So you can see that before you design an experiment, you really have to narrow down exactly what you want the experiment to tell you. It just can't be very broad. And step 2 is to determine the factors. Now, the factors are the explanatory variables that you're considering in the study. These are the things that can affect the response variable. Once the factors are identified, it must be determined which factors are to be fixed at some predetermined level, which is the control, and which factors will be manipulated, and which factors will be left uncontrolled. Step 3 is to determine the number of experimental units. As a general rule, we choose as many experimental units as time and money allow. Techniques exist for determining sample size provided certain information is available. In general, if you have time and money to spend on more experimental units, then more is better. But of course, we're always limited by time and money. So at some point you have to say, well, I need this many and I really don't need any more. Okay, then we determine the level of the predictor variables. For example, if the factor is a medication, the levels would be the different dosages you're going to test. If the factor is time spent studying, the levels would be the different lengths of time you're going to test. If a factor is beyond your control, you should randomize. Randomly assign the experimental units to various treatment groups so the effect of that factor is minimized. Each different combination of levels is called a treatment. Step 5 is to conduct the experiment. Replication occurs when each treatment is applied to more than one experimental unit. This helps to assure that the effect of a treatment is not due to some characteristic of a single experimental unit. It's recommended that each treatment group have the same number of experimental units. After the treatments are applied to each of the experimental units, we collect and process the data by measuring the value of the response variable for each replication. Any difference in the value of the response variable is assumed to be a result of differences in the level of the treatment. And then in step 6, we test the claim. This is the subject of inferential statistics, which we'll talk about in the second half of the class. But inferential statistics is a process by which we use information taken from a sample to draw conclusions about the population from which the sample was taken. And we've talked about this several times. This is the goal of statistics. We want to be able to use information that we get from a sample to draw some kind of conclusion about the population, something that we cannot measure directly. Okay, now let's talk about completely randomized design. A completely randomized design is one in which each experimental unit is randomly assigned to a treatment. And now we're going to walk through an example together of an experiment that is designed using a completely randomized design. And this is one of those examples where it's not something that I'm doing so that you can copy me later. It's something we're talking through so that you can understand. So we have here a farmer wishes to determine the optimal level of a new fertilizer on his soybean crop. Design an experiment that will assist him. Okay, so we're just going to give a for instance of each step. Identify the problem. Well, he wants to know how much fertilizer is best to use on his soybeans. So that's the problem. The farmer wants to know how much fertilizer he should use to maximize crop yield, and crop yield is the response variable. So we're going to apply a treatment of fertilizer or no fertilizer, and we're going to then measure crop yield. We want to see if the fertilizer, which is the treatment, affects the crop yield, which is the response variable. Okay, determine the factors that affect the response variable. Well, let's see. Think like a farmer for just a second. What are some things that can affect crop yield? We know for sure fertilizer does, and rainfall, of course, the quality of the soil, the amount of sunlight that the plants get, the amount of weeds that are growing in the nearby soil that are competing for nutrients, the pests that are in the location that might be destroying the health of the plant, and of course the plants themselves might start out either robust or sickly. So all of these things are going to affect our response variable, but we just want to measure the effect of the fertilizer. That means we either need to control the rest of these, or we need to randomize to minimize their effects. Now, some of them we can control, like we can control the amount of water that the plants get. We can control to some degree the amount of sunlight. That is, we can plant them in a sunny place, but then we can't control whether the sun shines or not. We can work to minimize the weeds, but of course that's not completely in our control either. We need to use the randomized design to help minimize the effects of the things that we can't control completely. Oh, and temperature is another one that is not really in our control, but certainly affects the crop yield. Now, the next step is to determine the number of experimental units, and this is something that, again, is a judgment call. More is better, but you don't want to spend too much time and too much money on it. You only have a certain amount of time to take care of these plants. So you can't have an infinite number. You just have to choose a number. There are rules about how to know how many is enough, but for right now, just assume more is better. We are going to go with 60 plants here. That's just what we're choosing for this example. And there's no reason for you to know why we're using 60. We're just happening to use 60 here. Okay, now let's determine the level of each factor. And this is another thing. I'm just giving you a for instance how this could be done. There's no right or wrong here. This is just something we're making up. So the factor is the amount of fertilizer. So we are definitely going to have a control group with no fertilizer. So we'll do 3 treatments, okay? We'll take our 60 plants and divide by 3, so each group will have 20. And so the first 20 receive no fertilizer, the next 20 receive a little fertilizer, and the next 20 receive a little more fertilizer. And notice how specific they're being. You can't just do like I did and say a little fertilizer. You need to be very specific so that you can track the success or failure of your treatments. And so here we're very specific about how much fertilizer and how often. Okay, now we're going to conduct the experiment. So remember, we started with 60 plants. We don't just need to take the first 20 that come off the truck and make them the control group, and the next 20 make them the low fertilizer group. We need to randomize, because maybe the first 20 came from a place where the plants were really healthy, and maybe the next 20 are not as healthy. We don't know, but we don't want that to affect our results. So we're going to use simple random sampling to assign each plant to a treatment group, and then we're going to apply the treatments, the 3 treatments that we had on the last screen, and record the crop yield at the end of the growing season. And then the last thing to do is to test the claim, and that's where you decide which treatment will give the best results. And there are methods for doing that, and that's what we're going to spend the second half of the course figuring out. Okay, now let's talk a little bit about matched pairs design. Matched pairs design is an experimental design in which the experimental units are paired up. The pairs are matched up so that they're somehow related. That is, you measure one person before treatment and after treatment. That would be a pair. Or you do the experiment on twins, where one twin is a control and the other twin receives treatment. Or you use a husband and wife. Or you have 2 similar people in the same geographical location. There are lots of different ways to do it, but these are just some obvious ones. There are only 2 levels of treatment in a matched pairs design because you've got 2 individuals. One is going to be your control and the other one is going to receive your treatment. So there's only 2 things, either treatment or no treatment. So here is an example of a matched pairs design for us. An educational psychologist wants to determine whether listening to music has an effect on the student's ability to learn. Design a matched pairs experiment to help the psychologist answer the question. Okay, so one solution is, and this is not the only way to do it, but one solution is that we could match students according to IQ and gender. For example, we match 2 females with IQs in the 110 to 115 range. And then for each pair of students, we flip a coin to determine which student is assigned the treatment of a quiet room or a room with music playing in the background. Each student will be given a statistics textbook and asked to study section 1.1, and after 2 hours the students will enter a testing center, take a short quiz on the material, and then we'll compute the difference in scores of each matched pair. Any differences in scores will be attributed to the treatment. Now, is it still possible that one student's good at courses like statistics and the other one's not? Of course it is. But that's why we can't just do it on one pair of students. That's why we need to do as many pairs as we can. And here's another matched pairs design experiment for us to look at. An ad for Crest White Strips Premium claims that the strips will whiten teeth in 7 days and the results will last for 12 months. A researcher who wishes to test this claim studies 20 sets of identical twins. Within each set of twins, one is randomly selected to use Crest White Strips Premium in addition to regular brushing and flossing, while the other just brushes and flosses. Whiteness of teeth is measured at the beginning of the study, after 7 days, and every month thereafter for 12 months. Okay, what type of experimental design is this? And our choices are completely randomized or matched pairs. And here, I think it's clear, since we have twins where one receives treatment and one doesn't, this is going to be a matched pairs design. And what is the response variable? Well, the researcher is trying to test the claim that the white strips will whiten teeth in 7 days. And it says the whiteness of teeth is measured at the beginning of the study, after 7 days, and every month thereafter. So the response variable is the whiteness of the teeth. And what are the treatments? Well, they either brush and floss and nothing else, or they brush, floss, and use white strips. So treatment A would be brushing and flossing, and treatment B would be brushing and flossing plus using the white strips. Okay, what are some other factors, controlled or uncontrolled, that could affect the response variable? Well, I can think of a few things that could affect the whiteness of your teeth. For one thing, age. Also, genetics and diet. You know, if you drink a lot of coffee or tea, your teeth are not going to stay as white as they would. Certainly, your genes have something to do with how white your teeth are. You know, there are medications that can affect the whiteness of teeth. Also, gender. Okay, now what might be an advantage of using identical twins as subjects in this experiment? Well, your identical twins are guaranteed to be the same age. They're guaranteed to have the same genetics. They very well might be on the same types of medicines. Identical twins are always the same gender. They were raised in the same home, so they probably learned to eat and enjoy about the same types of foods. So using identical twins in this experiment seems to help us minimize the effects of several factors that we can't control. So age, genetics, and gender will be the same in each pair. And there are several other types of experimental designs, and we've really just barely scratched the surface of it, but I wanted to give you at least a little glimpse of how experiments are designed. So now we've talked about some different types of observational studies, some different sampling methods, some ways that samples can be biased, and we've talked about some different ways that experiments can be designed. And I hope you see that statistics is not just calculating numbers. For statistics to really be useful, the beginning part, the data collection part, has to really be right. Otherwise, if you collect garbage for data, then you're going to get garbage for results. So this part, while it doesn't seem very mathy, it really can't be skipped over because we have to do this right in order to get it right at the end.